Good evening, all. Good evening, everybody.
Good evening, sir.
Make me a host, ma'am.
Yes,
Good
sir.
evening.
Sir, you can continue, sir.
Yeah, ma'am. All right. Okay, we will continue. Today we will finish with the chapter solids, so that from next class onwards we will start with the second chapter, solutions. Now maybe we have 20 questions and more than that. If you have any clarification, you can. I think 25 questions I have made. We'll work on these questions and then we'll see what can be done. Now, the first question is, which is the defect represented by the given figure? Which is the defect represented by the given figure? Schottky defect, Fresnel defect, vacancy defect, interstitial defect. What is this defect? You observe the figure carefully. You should have a cation here. You should have had a cation here. This cation from here, it is moved to the interstitial position. So when it's moved to the interstitial position, what kind of defect it is called as? Here there's a vacancy created. From this position, it's moved here. Tell me what kind of defect it is. It's a direct question. There is nothing to teach here.
The Fresnel defect.
It's a Fresnel defect. Okay, it's a Fresnel defect. Tell me what happens to density in the Fresnel defect. What happens to density in the Fresnel defect?
Sir, it remains constant.
Unchanged.
It remains same because the ion from here, it's moved here. You look at the volume remains same. The mass also remains same. Therefore, density also remains the same. When we say Schottky defect, the pair of ions will be missing from its lattice position. Now, for an example, if I have a cation, anion, cation, anion, if we represent like this, a perfect crystal if you represent, and if you observe an anion and a cation is missing, then we call that as a Schottky defect. You can observe here what I've drawn. You can see here there is an anion missing and here a cation missing. Since ions are missing, we know that density is mass by volume. Since ions are missing, what happened? Mass will decrease. Volume remains the same. Volume remains same. Therefore, what happens? The density also will decrease because the numerator decreases. Therefore, density also decreases. This is in case of what defect? This is in case of Schottky defect. Did you follow this? Yes?
Yes, sir.
The next question. What is the effect of Fresnel defect on the density? I taught you now. What is the effect of Fresnel defect on the density? The answer is what?
So,
The
density of the crystal remains unchanged.
Remains unchanged or remains same. It's a direct question. So if you will be very lucky if you have these kind of direct questions, no? And most of the time in chemistry, you'll have direct questions only, unlike physics and math. Or math you're not taking, okay. The next question. Alkali halides do not show Fresnel defect because cation and anions have almost equal size. There is a large difference in size of cation and anion. Cation and anion have low coordination number and ion cannot be accommodated in the voids. Now you should remember, in case of Schottky defect, the anion and cation, the size will be what? Different. The size will be different in case of what? Schottky defect. But in case of Fresnel defect, we learned in the theory, the anion and cation size almost remains what? The same. almost remains same. We have given more number of examples for the crystals undergoing Franklin defect as well as the Schottky defect. Can you give me one or two examples for the crystals undergoing Franklin defect and Schottky defect? Now, in case of Franklin defect, the examples is we can give zinc sulfide, we can give silver chloride, we can give silver bromide, we can give. All these, there is no large difference. Therefore, therefore they will not show what Schottky defect. But in case of, in Franklin defect, in case of Schottky defect, example is NaCl, KCl, all those. So therefore, the answer for this question is cation and anion have almost what equal size. When I say cation and anion, be more specific. Here, Franklin defect, I gave you NaCl and KCl. I never mentioned it as what? AgCl. Now the question is AgCl an alkyl halide? Alkali halide? Is silver belonging to the alkali metals, first group?
No, sir.
No, this is alkali halide. So alkali halides like Na plus and what? The Cl minus, they almost have comparable size. K plus and Cl minus almost have comparable size. Therefore, what happens is since they have comparable size, the ion will not move from its original lattice points and get into the interstitial position. It's not possible. Okay, if the size of a cation is very small, then they can get into interstitial position. If I say this is one layer, this is a second layer, this is a third layer, cation and anion, remember. Now, if the size of cation is small, then they can get into the interstitial position. But if the size of cation and anion is of comparable size, then it will not be in a position to get into the interstitial position. Therefore, it will not exhibit what Franklin defect. So you should remember, if alkali halide has to exhibit Franklin defect, the cations and anions should have different size. They should have a different size. Cation and anion. Cation and anion should be of different size. This is the condition, one of the conditions for the crystal to exhibit defect. Yes.
So, but AGBR shows both Frankel defect as well as Schottky defect.
AGBR shows. You know why AGBR shows? The atomic number of chlorine is 17. And silver atomic number, I don't remember. It's very high. It is in a D block element. It is above 50 or I think it's around 70. All right. Now just observe this. Now AGBR, when we say AG around 70, I think it's around 70. I don't know. I will just tell you now in a minute. Wait for a minute. I will tell you. I don't know how to. All right. I'll tell you. I'll tell you this. Where's that? Where's that gone, man? How do I come? How do I come to that? Yeah, I'll get you the size of AG plus. But you should remember the size of the atomic number of bromine is 80. The atomic number of bromine is 80. 1 minute, I'll give you atomic number of silver. Atomic number of silver. The atomic number of silver is 47. The atomic number of silver is 47. And for bromine, it is around 80. Now, these are comparably close compared to this. Not compared to this. But here the problem is the repulsion will be more. Here, in case of chlorine, the repulsion will be more. The atomic size of chlorine is small, therefore the repulsion will be more, and this becomes almost equal to the silver ion size. But here in AgBr, Br is already bigger. Therefore, there's huge difference between silver and bromine. Therefore, this shows Franklin defect also. I hope that you followed what I'm telling. Now, AgCl, I'll explain again. AgCl. Atomic number of Ag is 47, chlorine is 17. And here we have Ag plus and Cl minus. That means chloride ion has 18 electron. Due to the smaller in size, the repulsion of the electron becomes what? More. And therefore, it becomes almost a comparable size with silver. Therefore, it will show what defect? It will show a Schottky defect. But here in AgBr, almost one more thing you have to remember here is not only the size, the second is, I don't know whether you have learned in first 11th standard something called as Fajan's rule. Have you learned something called as Fajan's rule? I don't know whether you remember, but you should remember here, covalent nature of ionic compounds. Covalent nature of ionic compounds are explained by Fajan's rule. So ionic compounds can also exhibit covalent character. What do you mean by covalent bond? A bond formed by sharing of electrons. Smaller the size of cation, greater is the covalent character. Larger the size of anion, greater is the covalent character. Here, the larger the size, bromine. Therefore, the covalent character for AgBr will be more than what? AgCl. Even though it's ionic, it will have covalent character. Therefore, this AgBr shows both the Schottky defect as well as Fresnel defect. One is size. The next one is the covalent character. Two reasons are there for this molecule to exhibit both the Fresnel defect as well as Schottky defect. I hope we were convinced with it. Yes?
Yes, sir.
Yeah. Now, the fourth question is, which of the following crystal does not exhibit Fresnel defect? Which of the following will not exhibit?
So potassium.
KBr. Why KBr? Why KBr?
Sir, the size is small and it's almost the same.
The size difference is more. Potassium atomic number is 19. Bromine atomic number is 80. Therefore, the size difference is what? Maximum. There is a huge difference in the cationic size and what? Anionic size. Since that size difference is more, it will exhibit what defect? Schottky defect.
So Schottky.
It will show what Schottky defect. So therefore, this crystal KBr will not show Fresnel defect. So all the other will have a comparable size. Therefore, they will show Fresnel defect. Now, which type of stoichiometric defect is shown by zinc sulfide? Which type of stoichiometric defect is shown by zinc sulfide? The previous question we learned. Previous question. This is based on previous question. Here, zinc sulfide shows what? As per this, zinc sulfide shows what defect? What defect? Zinc sulfide shows what defect here? KBr shows Schottky. All the other molecules shows Fresnel defect. So size difference is comparable. Therefore, this will show Fresnel defect. It's a direct question. The next one is silver halides generally show. Silver halides generally show what question? Or what is that? A Schottky defect, Fresnel defect.
So Fresnel defect.
Both Fresnel and Schottky defect. Cation excess defect. Tell me.
So
you only ask me the question. You only ask me the question. You tell me the answer. Your answer is wrong now. AgBr is what halide? AgBr is what halide?
Yes,
is it not a silver halide?
Yes, sir.
Then in AgBr, you only ask me a question. It shows what defect? Fresnel defect as well as what you told. Schottky defect. Both it shows.
So, it says silver halides in general, right?
No, this is silver halide. How many silver halides you can have? How many silver halides? You can have AgCl, AgBr, and what? I and AgF. I don't know whether it exists. It's a smaller one. Only 3 you have.
Yes,
so amongst this one, AgBr shows both.
Yes, sir.
So therefore, silver halides generally show both the Fresnel and Schottky defect. The next question. An electron trapped in an anion site in a crystal is called as F center, Fresnel defect, Schottky defect, interstitial defect. What it is? An electron trapped in the anionic site in the crystal is called as what? It's called as what?
F center, sir.
Very good. It is called as what center? F center. Now, when I say F center, what does it mean? Now, if I have a crystal like this, I'm trying to draw and it takes time. That's the problem. If I draw like this, it's a perfect crystal. It's a perfect crystal I'm drawing. Now, what it says, electron is trapped in the anionic site. Anion means negative ion. Anion means what? Negative ion. This negative ion is replaced, and there's an electron trapped there. There's an electron trapped here. So this electron on heating can get excited. It can absorb the visible radiation, and then it can give a complementary color. So this is called as what center? F center. This F center is also called as what center we learned? Color center. It shows color. Metals show color due to the presence of what? Electron in the anionic site. So it's called as what center? F center. Next, which of the following will have metal deficiency defect? Which of the following will have metal deficiency defect? Which of the following will have metal deficiency defect?
Sir, FU, sir.
Why? Why?
Sir.
Why? I don't know from where you're getting the answer, but you tell me the reason also. Turning out the pages, tell me the answer. What's the oxidation state of iron? What's the oxidation state of iron? What's the charge on iron? Participate. Tell me, what's the charge on iron? It is Fe2 plus. Ferrous ions. Since I asked the question, you should not stop interacting with me. Talk to me. Fe2 plus. Now, when you say FeO, FeO will have Fe2 plus as well as it will have O2 minus. Fe2 plus ions and O2 minus ions. Now, metal deficiency defect. What is this metal deficiency defect? Now, I will write the structure again. A perfect crystal, I will try to write the structure. Now, when I've written the plus sign, it means it is Fe2 plus. Remember, it is Fe2 plus. It is not only one positive charge. It is two positive charge. This is a crystal. I'm drawing the crystal here. I'm drawing the crystal. This is a perfect crystal. Now, can iron exhibit in Fe3 plus state? Can iron exhibit in Fe3 plus state? We have, I don't know whether you have learned D block chapter in your school. D block elements will show variable oxidation state. Iron in 2 plus state will be called as ferrous, and iron in Fe3 plus state will be called as ferric ions. So D block elements generally will show more than one oxidation state. Therefore, it's called as what? A D block element showing variable oxidation state. Now, assume that one of the cation, see, I told you this plus sign indicates Fe2 plus ions. Fe2 plus ions. Now, assume that one of the Fe2 plus ion is, one of the 2 plus ion from here, it's occupied by an electron. And here the charge, instead of Fe2 plus, it becomes Fe3 plus. It becomes what? Fe3 plus. This ion is Fe3 plus. Now the charge is balanced again. The charge is balanced again. Now number of metal ions here is less, yes or no? Even though this crystal is what? Neutral, number of cations is less than number of anions, because I told you from this side, the cation is what? Missing. And in that position, what happened? An electron is trapped or the cation is missing. It can be a vacant site also. If in order to balance the electron charge, what happens is this gets what? Fe3 plus. All these are Fe2 plus. Here you get what? Fe3 plus. Now what happened? The charge is balanced. Now metal ion is lesser compared to what? Anions. O2 minus is more compared to Fe2 plus. Those kind of defects are called as what? Metal deficiency defect. Now why this is? Because iron can show variable oxidation state. Now sodium can show only one oxidation state plus 1. Potassium can show only one oxidation plus 1. Zinc can show only plus 2 oxidation state. Therefore, the sodium chloride or potassium chloride or zinc oxide will not show metal deficiency defect. The simple way to remember is any metal which can show variable oxidation states, they can show metal deficiency defect. Hence, the answer for this question is FeO. Followed?
Yes, sir.
Are you there in the class?
Yes, sir.
Others? Yeah, please interact with me. The next question. What type of crystal defect is indicated in the diagram given below? What type of crystal defect is indicated in the diagram given below? See this Na plus Cl minus, Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus. Here should be Na plus. Here should be Cl minus. Here should be Cl minus. This is Cl minus. This is Cl minus. This is Na plus and this is Na plus. So see, the equal number of cations and anions are missing. So equal number of cations and anions are missing from the lattice positions. Therefore, they will exhibit what type of crystal defect? They will show what type of crystal defect? Schottky defect. Density will decrease here in case of Schottky defect, remember. Next, which arrangement of electrons lead to anti-ferromagnetism? Which arrangement of electrons leads to anti-ferromagnetism? Anti-ferromagnetism. I don't know whether we learned anti-ferromagnetism. Anti-ferroelectricity we have learned. Anti-ferromagnetism. Yeah, anti-ferromagnetism we have learned. Just observe here. Now, one is upward spin, the other one is lower spin. Upward, lower, upward, lower. Now, what happens? Now, you can see one's upward, one is lowered, cancel. Upward, lowered, cancels. Therefore, the net dipole moment will be what? 0. So, even though we have unpaired electrons, the spins of the unpaired electrons are opposite. Therefore, the net dipole moment is what? 0. Those kind of properties are called as anti-ferromagnetism. Now, tell me in this one, which one will show anti-ferromagnetism? See, here it's up, 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 all are up. So it is ferrimagnetism. Here you can see
second one.
Second one. Here you can see it gets cancelled. So here the net dipole moment will be what? Is 0. Therefore, the answer for this question is simple. Direct question. It is second one. Okay. Yes or no?
Yes, sir.
Yes. The 11th question. The conductivity of germanium crystal increases on doping with gallium because occupation of lattice site of germanium by gallium, occupation of lattice site by gallium by germanium, of presence of extra electron in the lattice, none of the above. What it is? See, germanium is a semiconductor. Germanium is a semiconductor. Now, when we say germanium is a semiconductor, we can represent germanium like this. It also belongs to the carbon family. The valency is 4. Now, doping germanium by gallium. Now, gallium can be a pentavalent or it can be a trivalent. Pentavalent or it can be a trivalent. I don't know whether it's a pentavalent or trivalent. You can check that. Even though whether it's a pentavalent or trivalent, what is one will break, therefore conductivity will increase. The semiconductivity of germanium will increase on doping. So any kind of doping, whether it's a pentavalent doping or what, trivalent doping. So what it is, conductivity of germanium crystal increases on doping with gallium because what? Occupation of lattice site of germanium by what? Gallium. Here they have reversed. We are talking about the conductivity of germanium. So germanium, one of the atoms is replaced by what? Gallium. Therefore, what happens? Conductivity increases. Therefore, the answer for this question is option 1. Clear?
Yes, sir.
Yeah. Next one, doping affects the property of semiconductor. It increases the conductivity of semiconductor.
So option 1, sir.
Option 1, it's a direct question, increases the conductivity. So whenever you dope, whether it's a pentavalent impurity or a trivalent impurity, what happens is the semiconducting property increases. Therefore, it's a direct question. It is option 1. The next one, non-stoichiometric defect present in the sample of ferrous oxide with the formula Fe 0.93 and O1. This is Fe 0.93 and oxygen 1.00. Non-stoichiometric defect present in the sample of ferrous oxide. We learned it. I explained clearly. It is called as what defect? It's called as what defect?
Metal deficiency.
Metal deficiency defect, because I told you iron can have +2 or what, iron can have +3. I explained it very clearly. So the percent due to this property, see the ratio is not same. So ferrous ions will be what? 0.3 and the impurity will be what? Fe3+. That is why the ratio is not 1:1. Now, if I take NaCl, Na is 1 and sodium chlorine is 1. The ratio is what? 1:1. So if I take pure ferrous oxide, the ratio should be what? Fe2 plus and O2 minus. So it is also should be 1:1. But here in ferrous oxide, the ratio is 0.93:1 because of what? The ion undergoing oxidation or ion showing variable oxidation state. The impurity, the rest of the impurity, maybe 0.07% will be what? Fe3 plus ions. So therefore, the ratio is not 1:1. It has 0.93:1. So this defect is called as metal deficiency defect. Clear with this?
Yes, sir.
Yeah. Now to get N-type semiconductor from silicon, it should be doped with a substance with valency. Wait for a minute. Don't answer me. Dhanalakshmi, Ajay, Ritika, and who's the other person here? Other student answered me the question earlier. Tell me what type of substance to be doped in order to get N-type semiconductor?
Sir, is it 5?
Pentavalent impurity. See, silicon is a tetravalent. So it can have 4 bonds. So when you introduce a pentavalent impurity, like phosphorus will have 5 electrons. 4 electrons will be involved in bonding. The 5th electron will be free. So this electron which is free, electrons are negative charge. Therefore, it is called as what? Negative type, or it is called as what? N-type semiconductor. Therefore, the answer for this question is pentavalent impurities. So do not ever think of divalent and monovalent. It can be either trivalent or pentavalent. Trivalent will give you positive type and pentavalent will give you negative type. Charge-wise, P-type semiconductors is, tell me, charge-wise, P-type semiconductor is positive, neutral, negative, depends on the constant. Yeah, charge-wise, any semiconductor for that matter, whether it's N-type or whether it's P-type, it will be neutral. Charge-wise, see now I was talking about silicon here. In the silicon crystal, do we write Si 2 minus or 3 minus or 2 plus 3 plus, anything we write? No, silicon is a semiconductor. The electron is inside. As a whole, the semiconductor has no charge. Therefore, it will be what? It will be what? Neutral. Do not come to the conclusion just because we say positive type, it means what? The semiconductor has positive charge. N-type means the semiconductor has negative charge. No, the net charge in the semiconductor they're asking. The net charge is what? Always 0. That is why it is stable. Otherwise, it will be reactive. Therefore, the net charge here is 0. Therefore, we say it is what? Neutral. Followed?
Yes, sir.
Yes. The next question. Consider the following statements about the semiconductor. Silicon doped with electron-rich impurity is P-type. Silicon doped with electron-rich impurity, pentavalent impurity, it should be N-type. So therefore, the statement is wrong. Silicon doped with electron-rich impurity is an N-type. This is correct. Next one. Delocalized electrons increase. Delocalization means what? Movement of electrons increases the conductivity of doped silicon. That is also true. And electron vacancy increases the conductivity of N-type. So electron vacancy cannot be there in N-type. N-type already the electron is more. So electron vacancy is not possible. Therefore, this option is also wrong. The answer for this question will be option 2. The second and the third is right. Silicon doped with electron-rich impurities, an N-type semiconductor. Delocalized electron increases the conductivity of doped silicon. Followed with this?
Yes,
Students,
sir.
followed with this?
Yes,
Yeah.
sir.
Higher conductivity of P-type and N-type semiconductors is due to increase in number of positive holes and mobile electrons respectively, increase in number of electrons in both the types of semiconductor, increase in number of positive holes in both the types of semiconductor, none of the above. What it is? In P-type, what it is increasing? Electrons are increasing in P-type. In N-type, what is increasing? Positive holes are increasing. Correct? No, in N-type, it is what? Electrons increasing, right? Sorry. In N-type, it is electrons increasing, and in P-type, it is what? Positive holes increasing. Therefore, increase in number of positive holes and what mobile electron respectively are the reasons for higher conductivity of the semiconductors. Therefore, the answer for this question is option 1. Clear? Clear?
Yes, sir.
Yeah.
Yes, sir.
Tell me. Now here, germanium doped with indium, silicon doped with boron. Semiconductor formed above in the above cases are N-type, P-type, P-type, N-type, P-type in both the cases N-type. Now remember, indium is a pentavalent impurity. Now when we say indium is a pentavalent impurity, it will give what?
N-type.
N-type semiconductor. And boron is a trivalent impurity. Boron atomic number is 5. It's a trivalent impurity. When we say it's a trivalent impurity, it will give you what?
P-type semiconductor.
P-type semiconductor. Therefore, the answer for this question will be option 1. 18th question is option number 1. The correct statement. What happened? Sorry, something happened. Okay, the correct statement among the following is semiconductors have small energy gap between the valence band and the conduction band. Conductors have overlapped valence band and conduction band. Insulators have large energy gap between the valence band and the conduction band. All the above. What's the answer? This is a physics concept, but still you can tell me the answer. It's since we're talking about semiconductor, it can be asked in chemistry also. Tell me what will be the answer for this. Semiconductors. Now this is the valence band and this is a conduction band. The space in case of semiconductor is less. In case of the conductor, what happens? Valence band and the conduction band overlaps. But in case of insulator, the conduction band and the valence band, the energy gap is what? More. Electrons cannot delocalize. Electrons cannot move from conduction band to valence band. Valence band means the outer orbits. It cannot move. Therefore, this will be a non-conductor. So here, semiconductor, on increasing the temperature or doping, electrons can move from conduction band to valence band. But in conductors, it is overlapped. Therefore, electron movement, delocalization of electron is very easy. So what's the answer for this question? What's the answer?
All of the above.
All the above. You understood, right, what I'm talking? Ajay? Others?
Yes,
Are
sir.
you there?
Yes, sir.
Yeah, please. There's the next question. The magnetic substance that has lesser magnetic moment than expected is known as. Now we solve this question. You tell me the answer. No, we didn't solve. Magnetic substance that has lesser magnetic moment than expected is known as.
So paramagnetic.
Paramagnetic is only one unpaired electron. See, the question is, I don't know. I'll get back to the question. Now just observe this. Now, here we have how many unpaired electrons? 1, 2, 3, 4, 5, and 6. 6 unpaired electrons. If you remember, dipole moment can be calculated by the formula square root of n into n plus 2. N indicates a number of unpaired electrons. But here, opposites are there. They get cancelled. So expected is what? 6 into 6 plus 2. The value you can calculate. But here, since they're opposite, they get cancelled. But only 2 shows in the same direction. Therefore, the dipole moment will be lesser compared to what they expected. Because we all say that 6 unpaired electrons are there. Therefore, the dipole moment should be what? Maximum. But here, due to the opposite spin of few of the electrons, the dipole moment will decrease than the expected. Those kind of property is called as ferrimagnetic property. So therefore, the answer for this question will be what? Let's read the question and then answer. Magnetic substance that has lesser magnetic moment than expected is known as ferrimagnetic. I clearly told you. Antiferromagnetic, we learned the dipole moment is what? 0. Here the dipole moment is lesser than what? Expected. Paramagnetic means we have 1 or 2 unpaired electrons. Generally what? 1 unpaired electrons. Unpaired electron. Then we call that as a paramagnetic substance. Okay, more number of unpaired electrons are there, but the spin is opposite. Therefore, magnetic moment of few gets cancelled. Therefore, the magnetic moment is lesser than the expected. Those kind of property of a substance is called as ferrimagnetic. Clear with this?
Yes, sir.
Yeah, the next question. A ferromagnetic substance becomes a permanent magnet when it is placed in the magnetic field because all domains gets oriented in the direction opposite to the direction of the magnetic field. Domains are not affected by the magnetic field. Domains gets randomly oriented. All domains gets oriented in the direction of the magnetic field. All domains means what? All the electrons gets oriented in the direction of magnetic field. Therefore, a ferromagnetic substance becomes a permanent magnet when it's placed in the magnetic field. So all domains gets oriented in the direction of the magnetic field. Clear with this?
Yes, sir.
The next question, we will see. We are coming back to the different types of problems which we have to work. All right, let's see. The edge length of FCC crystal. The edge length of FCC crystal is 508 picometers. If the radius of cation is 110 picometers, the radius of anion is. We have not worked out this problem. Tell me, radius of anion. Now, I have a cation that is Na plus and Cl minus. I represent a cation like this. I represent a cation. This is a cation. And I represent an anion like this. Anions are bigger in size. Therefore, I represent an anion here. Now, if I say this is the diameter, the center, there's a nucleus, this is the diameter. Now, can I say this is R, this is R, this is R, and this is R? Yes or no? Yes or no? Yes or no?
Yes, sir.
What will be
Yes,
this
sir.
called as? What will be this called as? This will be called as what length? Edge length. Now, can I write like this? Edge length will be equal to twice into radius of cation plus radius of anion. Can I write like this?
Yes, sir.
Yeah. Now, edge length normally be represented by letter what? A. So I can write A is equal to 2 into R plus R minus cation into radius of anion. So we know that A they have given us what? In the question they have given A edge length to be 508 picometers. So I can write 508 picometers will be equal to twice anion plus R minus. So on solving this, what you will get? Radius will be equal to 508 divided by 2 minus of 110. On simply, this is mathematics. So 508 divided by 2, R will be equal to 508 divided by 2 minus 110 will be giving you 144 picometers. So the radius of the anion will be equal to 144 picometers. Did you understand why I took 2R plus 2R minus? Because I
Yes,
drew the
sir.
crystal here. Did you follow this? Others?
Yes, sir.
Yeah. Similar question this is. The edge length of NaCl crystal is, a unit cell is 564 picometer. If the size of chloride ion is 181 picometers, the size of anion they're asking. So same question, this is same similar type of question this is. So 2 into R plus R minus is equal to 564. So they're asking what is the cation. So we can write 2 into radius of Na plus radius of Cl minus will be equal to 564. So radius of the cation will be equal to 564 divided by 2 minus radius of the chloride ion, that is 564 divided by 2 minus 181, that will be equal to 101 picometer. That will be equal to 101 picometer. The answer will be option A. Is it clear? This kind of problem we didn't work. I hope that you're following.
Yes,
Correct?
sir.
Yeah. Now this is the next type of question. The distance between Na plus and Cl minus ion in NaCl with density 3.6 gram per centimeter cube is. They're asking you the distance. They're asking you the edge length. The density. So we know that density is equal to Z into M divided by A cube into Na. Now NaCl, what is the Z value for NaCl? You should remember NaCl crystallizes in FCC crystallizes. Therefore, Z will be equal to 4. So density, they have given 3.16. That will be equal to 4 into, we know the molecular mass of NaCl is 23 plus 35.5. That is 58.5. 58.5 divided by A cube into Avogadro number, we know 6.02 to 10 power 23. So on solving, you will get the value A cube will be equal to 122.77 into 10 to the power minus 24 centimeter cube. This is the value you'll get for A cube. So what will be A now? A will be the cube root of this. So cube root of this, you will get A will be cube root of 122.77 into 10 to the power minus 24. On simplification, you will get a value of 4.97 into 10 to the power minus 8 centimeter. That's equal to 497 picometers. So if you shift 2 decimals, you will get 10 to the power minus 10. That will be in meters. So 10 to the power, if you shift 4 decimals, if you see, this is like this. 4.97 into 10 to the power minus 8 centimeter. So if I write 497 into 10 to the power minus 10, it will be in what? Meters. So they're wanting in picometers. So it will be what? 10 to the power minus 12. Okay, so it's in picometers. Now they're asking, what is the distance? So distance between Na plus and Cl minus will be equal to A by 2. That is 497 divided by 2. That will be 248.5 picometers. 248.5 picometers. Hence the answer will be option B. So these many questions we have learned. You have any clarification, you can ask me quickly. Or else we'll work some more questions. I have to write some other questions. So till here, what we've done in the chapter solids, if you have any clarifications, you can ask me. One more question, maybe we will solve and then we will try to stop. If you have any clarification, you can ask me. You have any questions which are solved in your school and or college? If you are not clear with, you can ask me. Copper crystallizes in FCC with a unit cell length of 361 picometer. What is the radius of copper atom? What's the radius of copper atom? This is the question. Option A, they've given, option A is 157 picometers. B, it is 181 picometer. C, it is 127 picometer. And D, it is 108 picometer. Someone tell me the answer. It's an FCC. They're asking what's the radius? How radius and edge length is related for FCC? For FCC, remember the relation between the edge length and radius. For FCC, SC, and the BCC. For FCC, edge length is equal to 2 root 2R. Or we can write R is equal to root 2A divided by 4. It's all the same. Both are same. So that will be equal to what now? Root 2 by 4 into 361. So that will be equal to 127 picometers. The answer for this question will be 127 picometers, option C. Did you understand this? Did you understand
Yes,
this?
sir.
Can you tell me what is the relation between the edge length and the radius for simple cubic lattice? For SC, what's the relationship? For simple cubic lattice, edge length A is equal to 2R. For body-centered cubic lattice, remember this. For body-centered cubic lattice, A is equal to 4R by root 3. And for FCC, we learned it now. Our edge length A is equal to, we can write 2 root 2R. Or you can write this way also. So these three relations is a must to work out some of the problems based on edge length and radius. So any clarifications, quickly you can ask me. So this is the next question. This is the 25th question today, what we solved. So any clarification, you can ask me. See, kindly practice problems based on density, practice problem based on radius ratio, practice problems based on edge length, radius, all this. So different types of problems we have worked. And now maybe I'm just giving you one question. I'll read out the question. An alloy of copper, we have copper, silver, and gold, is found to have copper constituting the closed packing lattice. Copper constituting the closed packing lattice. If silver atoms are occupying the edge center, so copper has what? The CCP lattice. Silver atom are at the edge, and gold atom is present at the body. Gold atom is present at the body. They're asking you what is the formula of the alloy. What is the formula? Now remember, CCP means, okay, FCC. CCP refers what? FCC crystal lattice, face center, or center of the face. It is also called as what? HCP. In face center cubic lattice only, the packing will be maximum 74%. Remember, so don't get confused if they write HCP or CCP. It both indicates to you face, the center of the face. So copper atom is present at the center of the face. So when copper atom is present at the center of the face, what's the contribution for the copper atom at the center of the face? It is, what's the contribution? The number of copper atoms per unit cell in the face is what? 4. So number of silver atom in the present, what's silver atom? See, silver atoms are present at the edge. Each cube will have 12 edges. Remember, each cube will have 12 edges. We didn't speak about the edge-centered atoms, but I told you the contribution of edge-centered atoms is 1/4. And you should remember each cube has what? 12. So that will be equal to how much now? 3. And body-centered, we know it is what? 1. So it will be what? Cu4, Ag3, and Au1. This will be the formula of the alloy. Did you follow this? I'm not able to write this complete question here because of the lack of time and not need. So this problem also you have to remember. These are some of the questions what we did today are questions which was asked in the previous papers. So with this, we are going to conclude with the chapter solids. We will continue with the new chapter solutions in the next class. Any clarifications? Quickly. We will not have time to get back and revise this chapter later. If you have any clarification, you can ask me now. No clarification? Ma'am, can I leave the class? Ajay, can I leave the class? Dhanalakshmi, Ritika? Can I leave the class? Nobody is talking. Can you hear me at least? Huh?
Yes, sir, you can leave, sir.
Yeah, okay, thank you.